madness. Maybe so, but it's not half as mad as the idea that brought us to this point.
You are staying...
Is there such a thing as a higher dimension? A parallel universe where otherworldly things can happen? Over the years, artists, writers, and filmmakers have tried to answer that question, creating some dazzling works of science fiction in the process. But are the higher dimensions we see in sci-fi really fiction? Meet Maggie, scientist by day and sci-fi fanatic by night. Maggie's watching a 1950s film about scientists who invent a device that catapults them into the fourth dimension, where they can walk through walls and read minds. Like the rest of us, Maggie lives in a three-dimensional world, but she also appears to have an interest in alternate dimensions. In 1940, master sci-fi author Robert Heinlein wrote the short story, And He Built a Crooked House. In the story, our hero builds his home from an unfolded four-dimensional hypercube. When an earthquake strikes, the house folds up, creating the world's first four-dimensional house, where occupants can look down a hallway and see their own backs. Dimension is one of the most important and intriguing ideas in mathematics. We move in 3 dimensions of space. We live in 4 dimensions of space and time. But mathematicians and increasingly scientists of all flavors, from statisticians to biologists, are finding that they need to understand and work in worlds of hundreds and even thousands of dimensions. Worlds that reach well beyond human sensory experience. When we start asking questions such as, when did our universe begin and how will it end? Many scientists believe the answers will involve 10, 11, 12, or even more dimensions. But what do we really mean by the word dimension? Generally speaking, the dimension of space or a problem is simply the number of numbers that we need to describe the situation. These numbers are called coordinates. The idea of coordinates was developed in 1637 by French mathematician and philosopher René Cartesius Descartes. Descartes, who never got up before 11 a.m., as the legend goes, was lying in bed watching a fly crawl across the ceiling, and it hit him, the basis for what we now call the Cartesian coordinate system. What Descartes very well could have realized by watching that fly wander across the ceiling is that the fly's position on the ceiling could be described by exactly 2 numbers, what we might call the x and y coordinates. Now, I have a feeling Descartes would have loved one of my favorite toys, the Etch-a-Sketch. It's all about coordinates. With one of these knobs, I can control the lines that go back and forth, the horizontal direction. And with the other, I can control the up and down, the vertical dimension. We can make some pretty pictures with this toy, but our freedom of movement is limited to just these 2 independent dimensions, or parameters we might call them. Now, of course, we don't move in a world of 2 dimensions like the Etch-a-Sketch. We're able to move not just side to side and back and forth, but up and down as well, so that we need 3 numbers to describe a point in our physical world. So suppose we had a 3-dimensional Etch-a-Sketch. Well, let's not suppose. I actually have one. Come on, let's see it. Here's my 3-dimensional Etch-a-Sketch. Now with 3 knobs, I can draw vertically, horizontally, and with depth. This is so cool. I now have 3 independent parameters so that I have freedom of motion in 3 dimensions, just like in our everyday world. But in the world of mathematics, we deal with dimension in some rather unique ways. In fact, when mathematicians talk about dimension, we're talking about more than spatial dimension. We're talking about any set of parameters that help define everything from the markets to the health benefits of a particular muffin to the latest model car or even the perfect date. Our friend Maggie is using a computer dating website circa 2007. It starts by asking a series of 250 questions grouped into 30 categories. By the time Maggie's done, she will have established values for 30 different parameters to define herself, as well as her dream date. With these coordinates, you can now say we're in a 30-dimensional world. And in this world, each point represents a human being. And if Maggie can find someone whose coordinates are near hers, she's got a date. When we're talking about sets of parameters, it seems we can work in as many dimensions as we want. But what's so special about 3 dimensions? Because we live in a 3D world, our brains think in 3D. But can we actually see things in more than 3 dimensions? What would a 4-dimensional object look like? Well, 3-dimensional etch-a-sketches, but multi-dimensional personalities. Can we see those kinds of things? We're here with Greg LeBone, research mathematician at Dartmouth College. And Greg, can I see 4 dimensions without hurting myself?
Well, you're going to have to go through a little bit of pain, I think, to see into higher dimensions. But the pain comes in the form of analogies and metaphors. So we would probably start understanding 4 dimensions by thinking a little bit about what we know in lower dimensions.
Okay.
For example, we could start with the cube.
Okay, great. Great. We've got our cube.
We've got our cube here. And there's a few things worth observing. First, that looks like a 3-dimensional cube to us.
Right.
But of course, this is on a 2-dimensional screen. This is some sort of projection.
That's true. That's true. It's a total cheat.
But our brains are, fortunately in this case, very hardwired to interpret this as a 3-dimensional object.
Right.
4 dimensions is much trickier because, for example, here's a picture of a 4-dimensional cube that we'll just look at for a second just to get a sense. It looks very cluttered. It's the same sort of projection where now we've gone from a cube in 4 dimensions, we put it on our screen down here in 2 dimensions, and it looks very cluttered. What it would be like as a 2-dimensional being to experience a 3-dimensional object. Because what we are is essentially, in the way we think spatially, 3-dimensional beings, and we're contemplating a 4th-dimensional object. Now, this is not a new idea. Here's Flatland. This is a very famous example of this, put into a beautiful story.
So this is Edwin Abbott's Flatland, a book first printed in 1884, and it's the story of beings that live in 2 dimensions, on the plane, if you like, with no thickness, and how they might experience 3-dimensional life, and which is analogous to our problem as beings living in the 3-dimensional world trying to experience 4-dimensional life. So the 2-dimensional being is living on this sort of infinitesimally thin surface.
That's right.
So they can only move in 2 dimensions.
And somebody enters their world from above. A sphere, we can imagine. A sphere is this very symmetric object. And we're going to imagine it in the following sense. This sphere, which actually lives in 3 dimensions, is going to dip into this 2-dimensional being's world. And the 2-dimensional being is going to experience an aspect of the sphere, what we think of it mathematically as slices of the sphere, and they're going to look at the geometry of those slices over time as the sphere moves through their world, and they're going to use that as a summary statement as to what 3 dimensions looks like. And as the sphere dips through the space, of course, this point instantaneously blows up into a little circle. Because as this sphere dips into the plane, it grows, it gets to some critically large length, which is, of course, the equator circle of our sphere, and we see it comes back and it shrinks back down to a point. And so what has the person experienced who lives in this plane is a little movie of some circle getting bigger and collapsing back down to a point. And this is their way that they're going to initially think about the 2-dimensional sphere that lives in 3D that we're used to. Is they're going to think of it as a bunch of slices at different times, and they're all put together by the continuity of time into an object. And we see that object here because time we can think of as our 3rd axis, our 3rd dimension here. As it dips through there, that dimension changes.
There's a sense of, so there's a sense in which we see the movie all at once, but they have no ability except to see one frame.
That is exactly the analogy that we want to have in mind. Because now we're going to imagine looking out into our room. Here. And now we're going to have something that starts off as a point. It expands into a sphere. It reaches some critical size. It shrinks back down to a point. And what have we just seen? Well, to us, we just saw a movie of a little explosion and contraction of some kind. And we're not sure what we've seen. Now, it could well have been that the 3-dimensional sphere in 4 dimensions has just dipped into our world to give us a visit. Okay? And now we understand that analogy because we can experience exactly what happened in the 2-dimensional case. And that's the power, of course, the Flatland analogy is that now something that we can witness in our world, we can now understand that via this analogy of what the Flatlander experienced. So what you have just experienced is an object that lives naturally in 4 spatial dimensions. The 3-dimensional sphere in 4 spatial dimensions could be thought of as this little movie as you might experience it, and as our Flatlander did experience it. The problem is we can't step back and see the movie all at once.
Yes.
Okay, and we don't do that very naturally. But using this analogy, we can get a grip on what higher dimensions might, well, how they really do look in our lives.
Right, and and a way to start to begin to think about them as mathematicians.
That's correct. So now maybe we should go to the more fun object, which are these cubes.
Great.
Okay, so now let's imagine, once again, we're in our Flatland world, and now a cube is going to dip into this world. It's nice to look at this trivial direction where it comes in, and all of a sudden, instantaneously, we see a square in our two-dimensional world.
Right.
It floats through, and it's totally static looking. It looks like a static square that just suddenly disappears.
Yeah. So now we can get a different view, or we can let our Flatlander get a different view of the cube by actually changing the way in which the cube comes into his world, right?
That's right. That our original way where it came down with the flat parts first gave us this boring movie, and in many ways, sort of a boring look at the cube as a three-dimensional object. It's gleaning very little from it.
Right.
But if we bring it down from another angle, the Flatlander learns a lot about the geometry of the shape. So let's come down vertex first.
Yes.
And as we come down kind of at a slight angle here, but we can watch it on the screen, this vertex, when it comes down, first he sees a point, just like in the spherical case, a point. But that point, rather than exploding then into a little circle, has now become a little triangle.
Right.
Okay?
Yep.
And this triangle, we lower it down, every time one of the vertices of our cube in 3 dimensions hits it, an edge is born.
Yes.
And we see this birth process of these edges as our triangle changes into this quadrilateral, which first has this very short side, which gets longer.
Right.
And then it changes into this pentagon-type shape, 5-sided object, into this hexagon. And now, of course, this hexagon has gone back to a pentagon, or a pentagon-type object, 5-sided, then to this quadrilateral that we see, finally going down to this triangle and a point.
Yes.
So it's a lot like the sphere case.
Greg, what I like so much about this discussion is that it's actually part of things that happen in the real world all the time. For example, when people are trying to image your body, they actually do it by constructing slices of you using some kind, like X-rays or whatever it is, and they rebuild your body from those slices. And the other way in which it's come up is in Cubist art, in fact. And Picasso's idea when he was creating this was actually inspired by discussions of how to see 4-dimensional things as 3-dimensional slices, which is how we're actually going to try to see 4 dimensions, like the Flatlanders try to see 3.
Absolutely. So it's easy to see how art and this would interact in the sense that your understanding here is very much so a metaphor in the same way that the art might be used. But let's look at it and see what we're talking about. Here, we're going to be playing that same exact game where we dipped our cube into the Flatlanders world, but we're going to dip a hypercube into our world and see what we see. The cube that lives in 4-dimensional space, at least a projection of its. So what are we watching? We are watching a 4-dimensional object dipping into our world. Here it starts. We get our vertex. As it dips in, now we get to a simplex, a tetrahedron, with 4 vertices as it comes in the corner. And now watch it evolve as it hits these corners. The vertices are chopped off, and we get these things that have faces that look like our original
and a perfect analogy to what was going on for the Flatlanders.
And now we go through the whole sequence, and we see that shape changed over and over again until we're back at our vertex. And we have a beautiful movie that captured